So in this section, we come to angular acceleration, and we're going to use the analogy like force equals mass times acceleration. Remember, the analogy for force in rotational motion is torque, yeah? So the net torque is equal to something, I'll talk about this I later, I times alpha, where alpha is the angular acceleration. So let me write here the analogy, and you know that well. You can write it as F net, or you can put a summation sign, which means the net force, that external force, m into a. This is Newton's second law, right? And analogous to this is the torque. Analogous to acceleration is the alpha. Remember, we've seen this before. And analogous to the mass is the moment of inertia, okay? So inertia is slightly different from mass. And we will see what moment of inertia is. Okay, so I stands for the moment of inertia. It has to do with the distribution of mass about the axis. Okay, so it's not as simple as mass. Remember, mass was just a scalar quantity which is inherent to the object, right? But moment of inertia is not. It changes depending on which axis the object is rotating about. Okay, so we'll see more about moment of inertia in a minute. You can get problems like where you have a combination of rotation and translational motion. So here we have a pail that's going to be lowered into the well, and it'll come up with some water. And this is a pulley which has a rope around it. Okay, so the two move at the same rate, yeah? While this is rotating, this one is just translating. This is just going up and down. So we're going to make free body diagrams. These are two connected objects. Think back to, I think, chapter 4, where we did connected objects towards the end of it. And you're going to draw free body diagrams for each object. This one has its mass mg acting downwards and the tension in the string upwards. So these are the only two forces on it. When the tension is greater, the bucket is going to move upwards. When mg is greater, it's going to move downwards. Yeah? If they're completely balanced, then it's in equilibrium. What about this pulley? We know the pulley rotates because there's a force, which is the tension on the string, acting at this distance r away, which is the radius of the pulley. So that's here. So T here is my force times r. This is going to produce a torque. And remember, torque produces a change in rotation. So if it was stationary and you produce a torque, it's going to start rotating. The other forces on this disk are its weight, mg, acting downwards, and the normal reaction from the rod, which is upwards. So these two are going to be equal and opposite. It's really this force causing the rotation. So in one case, we're going to apply Newton's second law in translation. In this one, you're going to apply the rotational version of it, tau equals I alpha, okay? And sometimes you might need to remember and use the fact V equals R omega. Remember those relationships, the three relationships between the fundamental quantities we use to derive the expressions for kinematics. So displacement, angular velocity, and angular acceleration, and how they were related to the linear quantities through multiplication by R. Yeah? Linear equivalence. Okay. So a little more about moment of inertia. In general, moment of inertia is defined, so three signs in the equal summation of mr squared, where m is the mass of the objects, r is the distance from the axis of rotation, and we're going to square that. So the units are going to be kg, meter squared, okay? It's analogous to the mass in the sense that this offers the resistance to change in motion when an external torque is applied, yeah? It's different from mass in that it depends on the distribution of the mass about the axis of rotation. So the values of m and how far they are from r, which is the distance from the axis of rotation. If you consider a hoop like this, so all this is empty space in between, this is the center of the hoop, and it's homogeneous, so the mass is equally distributed everywhere, uniform density. Then if we take equal areas or equal volume here, they will have equal masses, M1 equals M2 equals M3, and each one, say this blue area M1, produces a moment of inertia of M1 R squared. Yeah? This produces a moment of inertia of M2 R squared, M3 R squared, and each one of these are equal. Yeah? And it depends how many divisions you make. If you make I divisions, you're going to get MI, RI squared. Yeah? Well, RI is just the uppercase R. They're all equidistant away, one radius away. So we can take that radius in common and we get the sums of M1, M2, M3, and so on, which is the total mass of the hoop. So we see that the moment of inertia of the hoop about an axis through its center is mr squared. Yeah? Now consider for a moment what would happen if we took the same mass, which this hoop has, but now we thinned it out so that it filled in all this area. So we get a thin disk, yeah, which is uniform in density everywhere. Would my moment of inertia increase or would it decrease compared to the hoop? You want to consider now where the mass is with respect to the distance from the axis of rotation. If the masses come closer, then some of the masses closer, this value is going to go down because R is smaller for some of them. Okay, so indeed that is the case. If it's a disk, right, a thin disk, you are going to actually get 1/2 mr squared, a disk rotating about an axis through the center. Okay, and here we have the disk. Here its axis of rotation going through the center. Get 1/2 mr squared becomes your formula. If you shift the axis so that the entire disk rotates about an axis on the edge, so your entire disk is now going round here, then it's going to be greater than this because now you have some which is further away, which is almost 2r away. Right? The mass up here is twice the radius away from the axis of rotation. So indeed, this is greater, 3/2 mr squared. Okay. And we're not going to derive, but there are several objects, and you need to know some of their things. You need to know the general expression, which we saw a couple of pages ago. So you need to know the general expression for moment of inertia. If you have one mass, that's going to be the mass times r squared, which is r is the distance from the axis of rotation. If you have more than one mass, you simply add each moment of inertia together to get the total sum. So you need to know the one for the hoop, okay, or hollow disk. You need to know the one for a solid disk through the center of axis of rotation, center of symmetry. You don't really need to know this one. You also need to know the value for a rod when the axis is through the center, which is 1/12 ml squared, where L is the entire length, yeah, and the rod with the axis shifted to one end. So now some mass is much further away. We expect this to be larger. And indeed it is. It's 1/3 ml squared, right? So 4 times this. Okay. You don't really have to memorize the ones for the sphere and a hollow sphere and solid sphere, but these are just here to show you that similar reasoning can be used in these cases. And you should do that to convince yourselves. Here's a hollow cylinder, here's a solid cylinder, and you need to be able to figure out which one has the greater moment of inertia. You may not need to know the exact formula, but you do need to know which one has the greater moment of inertia. Okay, so let's do a problem on this. Consider a father pushing a playground merry-go-round. There he is, they gave you the diagram. He exerts a force of 250 newtons at the edge of a 50 kg merry-go-round, which has a 1.5 meter radius. So this R here is 1.5. We know R, we know F, hence we know the torque, right? So let's write the torque. Just a second. Okay. So torque equals R cross F, or RF sine theta. What is the angle between the R and the F? The angle is 90 degrees because the force is applied along the tangent line, and this is the radial line, yeah? So you need to calculate the value of the torque, yeah? Using the 250 newtons and 1.5 meter radius, sine 90 is what? Okay. Calculate the angular acceleration produced when no one is on the merry-go-round. So we can get this number, and we also know that tau equals I alpha, right? This was our definition for angular acceleration. So we need to find alpha, which means we need to divide this quantity by I. Yeah, so we need the moment of inertia. And we're going to treat this like a solid disk. Yeah. So our formula for solid disk was 1/2 mr squared. Now this is our moment of inertia times alpha. We know m, it's given as 50 kgs. We know r is the same 1.5. So you can set this equal to this, and you can calculate alpha. Okay. Part B, when an 18 kg child sits 1.25 meters away from the center, consider the merry-go-round itself to be a uniform disk with negligible retarding friction. So if a child comes on, and let's say the child sits here, and that distance is 1.25 meters. And the child has a mass of 18 kgs. Yeah, that means they're exerting a force mg downwards. So we need to now add to the moment of inertia of the disk, okay, which was this, 1/2 mr squared, the moment of inertia due to the child, which is going to be mr squared, right? So the moment of inertia due to the child equals 18 times 1.25, which is their distance, the child's distance from the axis of rotation, this being the axis of rotation up here, squared. Now you need to add this term to this term here before we multiply by alpha. So your I, total I, has changed. Your total I is the I for the disk originally plus the I for the child. So it's the only difference in the second part. Let's just make it further clear that this is just the disk. This is part A, and this is part B. Okay? So with all these hints, you should be able to work it out. Once you've worked it out, move on to the next page to have a look at the actual values and compare. This is part A. You're going to get alpha as 6.67 radians per second squared. Remember, this is acceleration, so it's going to be in units of radians per second squared, angular acceleration. And in the second part, your angular acceleration is going to go down, yeah, which is what you would expect because now there's greater inertia. So 4.44 radians per second squared.